In this video, we'll talk about how you can go from equipotential lines to electric field. So we have seen, in this video, I'm gonna show you the connection between this way to represent potential, and I will show how you can use this information here to find the electric field. Okay, it is often, and it is useful, it is helpful actually, to have the equipotential lines or the equipotential surfaces, and from those to think about the electric field. Now, in which cases is this useful? If I want to think about forces, if in what I'm trying to do, forces are useful, if electric forces are useful for me to understand why my system behaves the way that it does, then I will have to work on this process. If I'm looking at the equipotential lines and I need to see what the forces are, then I have to go from potential to field, and from the field I can use the force equals Q times E to think about the forces. So this is when this process is useful. Now, here are the two things that you need to keep in mind to go from equipotential lines to electric field. The electric field is always, I'm going to write them here. The field is always perpendicular to the equipotential lines or surfaces, whatever you have. And the second thing, let's say before I go there, let me illustrate what I mean with that. So here, if I look at this equipotential line, then the electric field vector would have to be perpendicular to this at this point. Now, perpendicular could really mean two things. It could point that way, the electric field, or it could point that way. Okay, but I do know that it has to be perpendicular to the equipotential line, so it will have to be one of those two options. And then here it will have to be perpendicular again, so it will be either that or that, and I can do the same thing for the other ones. Always perpendicular to the equipotential. If it is here, it would have to be either this or that. Now, I want to talk about how will you know whether it's this or that, which one of the two arrows is the correct one. I want to remind you from a previous video that I talked about the sign of the potential difference, determining fast the sign of delta V if you know the electric field. What I showed you back then, if you move in the same direction as the electric field, the potential decreases. Now look here. In which direction is the potential decreasing? From 2, 1, 0, minus 1. So the potential is decreasing that way. And for me to decrease potential, I have to move in the same direction as the electric field, which means this is my electric field, not the other one. So I do have to erase this, and I'm gonna do it again from the beginning actually. So my electric field is actually this one, perpendicular to the equipotential line, and if you move in the direction of the electric field, you are decreasing the potential. So here it's gonna be something like this, and then here it's gonna be something like that. Okay, always perpendicular to the line, and if you move in the direction of E, you will decrease potential. Now, this was the first rule. The second one is that the strength of the magnitude of the electric field is proportional to the density, to the equipotential line density. Now, what does that mean? So, let's say I'm gonna do it here. I know that the electric field will point more or less in this direction, and I know it's gonna be perpendicular to that. Now, look at this. I can also tell if I look at this area versus, I'm gonna try to do a similar circle here. Okay, this circle includes only one equipotential line, but if you look at this circle, which I try to do the same radius, it includes more equipotentials. Here I have two. Or you can, it may be easier for you to look at the density of the equipotentials. Here in this space, you have more equipotentials in the same area compared to what you have here. Here you have less equipotentials in the same area. So the density here is less, the density of the equipotentials here is greater. Now, according to the second rule, if you have a greater density of equipotentials, the strength of the electric field is greater, which means I need to draw a longer arrow for the electric field. Perpendicular, always perpendicular to the equipotential, but a greater arrow. Okay, so this is E, perpendicular. Trying to do a longer arrow, E. Okay, perpendicular. So this is these are the two properties of equipotentials that help you define the electric field vectors, that can help you find the electric field vectors. Now, I'm gonna close here. When you have equipotential lines, these two rules are the only things you need to know in order to determine what the electric field looks like in that area.